Howdy, in this example, we're gonna go over beam deflection. What do we have in this problem? We have a shaft. There's 2 point loads being applied. And we wanna determine the deflection at point A over here. They tell us that the shaft has a diameter of 100 millimeters. There's no mention of inside or inner diameter, so we're gonna assume it's a solid round shaft. They tell us that it's made out of steel and it has an elastic modulus or Young's modulus of 207 gigapascals. If you ever encounter a problem where we just tell you steel, aluminum, bronze, remember that you can always reference the appendix C1 on your equation and reference booklet. Looks something like, I don't know if it's showing. Appendix C1. And it's going to give you the different materials, so you want to look for the modulus from there. Anyways, just like we talked in the presentation, the method that we're going to use here is superposition, where we look at the problem and then we're going to look or divide it into the individual contributions of each type of loading, right? So here we have 2 point loads. So we're going to look at what is the deflection at point A caused by the load at point A, figure out how much that is, and then figure out what is the deflection from the loading over here in the second pulley at point A. And then depending if both deflections are down, we're going to add them together. If they're going opposite directions, we're going to take the difference. And that way we can determine the final deflection. Again, this is method of superposition. And this figure, I already went ahead and did that. So I already have a drawing over here with the point load at A. And I have another drawing with the point load at the second pulley. So again, we're saying the sum of these two is the same as this one over here. So now our job is just going to be to look at the shaft over here and determine which equations that we're going to use. Remember, in the back of the booklet, we have a bunch of equations. If you remember, we have equations for cantilever beams. So that's whenever a beam is fixed at one of the ends. Next, we have a table for simply supported beams. And then the last table, Appendix D3, is for beams that are fixed on both ends. When we look at this one, we have a bearing. And if we pay close attention to the geometry of the bearing, this one typically signifies a journal bearing. And this one's a thrust bearing. So if we were doing the statics on, this one, right? A journal bearing is just gonna have a reaction in the Y direction. So something like this. A thrust bearing can have reaction in the Y and reaction in the X. So what we're saying is this is no different than, for example, having a beam with a roller and a pin connection, right? This is what we call a simply supported beam. Anytime you have a pin and a roller, it's called simply supported. If you remember, why is it simply supported? Well, because the constraints over here, in this case, a roller and a pin, or a journal bearing and a thrust bearing, just gonna give us 3 unknown reactions. This being 2D problem, we have 3 equations of equilibrium, right? Some of the forces in the X, some of the forces in the Y, and some of the moments. So we can simply determine what are the reaction forces at the supports. That's what we call these simply supported beam. Alrighty, so when we look at this one over here, what do we have? We have a simply supported beam, but the load is acting at this end over here. So if we look at Appendix D2, we could look at case number 4. That's the case for overhung load. So that's what we're gonna overhung load. If we look at the drawing over here, it has something like this. So it has a beam, reaction down, reaction up, and then with the load at the end. So there's a load over here. This would be the load. Usually they call them P. And they also give us what the deflection of the beam is going to look like. So it's going to look something like this. Come down like so. And then they tell us that at the end over here, so that the maximum deflection is going to be at the tip. And that equation for the max deflection is P times B squared times L divided by 3 EI. So all we have to do on this one is look at the figure and determine, okay, what is B and what is L? And if we look at the figure, we can see that for this case, L is going to be the length of the beam. So all of this here. And B is going to be the length of the overhang from the support to the load B. I'm sorry, to the load P. Well, when we look at this one, remember, we're using this overhang load to solve for this guy. Here we have the supports, we have the load, but now on this figure, it's the load is towards the left. On this one, the load is towards the right. And basically, so what we have to do for this one is, you can think of it as two ways, right? Let's say there's a person standing here, like just like we're watching, and then there's someone in the back of the paper looking like towards the camera, right? That person would see something like this. That's one way to look at it. Or the other one is just to say, hey, we can use this equation, right? But we're looking at a mirror, right? So this guy is completely mirrored in this direction, right? So for our problem, L is still going to be the whole length of the beam. So L is going to be, in this case, it's 1.5 times 3 or 4.5 meters. And B is the distance of the overhang. So B is 1.5 meters. So we have our B, our L. P is the load, which in this case, P in this one is 6.5 kilonewtons. Right, so we got P. 3 is a constant. E is our Young's modulus, 207. And the last thing that we need is I, or, sorry for moving that. And if you remember, I is the moment of inertia. Again, if you don't remember, you can look at Appendix B in your equation booklet. Appendix B is going to have properties of sections and solids. And it tells us that the moment of inertia for a circle is just pi times the diameter to the fourth divided by 64. So pi d fourth by 64. Okay, so why don't we just go ahead and calculate I on this one. So it's going to be pi times the diameter. Remember, the diameter here is 100 millimeters. So here I hesitate a little bit because I'm going to use this I in this equation, right? And what else is in there? There's B, which is the overhang length, and L, which is the length of the beam, and meters. So I'm just going to go ahead and calculate I in meters, right? So 100 millimeters in meters is just 0.1 meters. And then I'm going to move this one to the power of 4 and then divide the whole thing by 64. And this gives an I of 4.9087. And I want to carry about like 4 decimal places over here, or 4 digits after the decimal, just because these deflections usually are very small numbers. So I don't want to lose precision there. So 4.9087 times 10 to the minus 6. And since D is in meters, this is going to have units of meters to the fourth. Okay, so now we have I. So now it becomes just a plug and chug. So let's go ahead and calculate this delta max over here as P. So 6.5 kilonewtons, or 6,500 newtons, times B. B is 1.5 meters. Remember, we're going to square this one, times L, which is 4.5 meters, and then divided by 3 times 207 giga, or 207 times 10 to the 9 newtons per meter squared. times I, which we said was 4.9087 times 10 to the minus 6, and this is meters to the fourth. So let's go ahead and plug this to the calculator. I have 6,500 newtons times 1.5 squared, squared times 4.5 PBL divided by 3 times 207 e to the 9 times 4.9087 e to the minus 6. And the number that comes off of this one is 0.2158. So 0.0215. There's 9, so I'm going to round this to a 9. Right? And the unit is going to be meters. Or we can move the decimal point 3 places, right? 1, 2, 3. And this becomes 21.59 millimeters. Now, which direction is it? Well, let's look at our figure, right? We have our load coming down, and so the end of this beam is going to deflect down 21.59, right? If we put the deflection curve on this one, right, it's going to look like this. This arrow pushes the beam down, so it goes down. This support has to push back up, so this goes down, is going to push it back up, and then this one's going to bring it actually down like this. So this is what we just calculated from that delta max. It's 21.59 down, but we're still not done. We still have to calculate the contribution from this load over here at 0.8. What do we have over here? Well, we have a simply supported beam, right? And if we look, pay attention here, the load is right smack in the middle. So we can look for the case for a simply supported beam with the load at the center, right? And if you look at that table, right, it's going to tell us, hey, we can calculate the deflection at the center, or we can calculate the deflection at any point, right? How is this beam going to deflect? Well, if I have a load going down and is right smack in the middle, this is going to kind of make that shaft or this beam kind of smile like this, right? We have equations. If we look at the equation booklet, we have equations for anywhere here in the middle. We have the maximum deflection, which happens at the center. But in this case, we want what's happening over here at this end. So instead, what we're going to do is we're going to do a little trick, right? So we know that the beam deflects down like this. It's going to flex like this. However, we're looking at 0.8. So all we have to do now is we realize that if we neglect the weight of gravity, right, then this section over here is just going to remain straight over here. And I wish I was in class so I can show you with a ruler, you can see this. But anyways, right, this is, I'm like exaggerating the deflection. So instead what we're going to use is we're going to use the equation for the slope at the ends for theta. And if we look at this one, slope at the end for theta is going to be equals to PL squared by 16 EI. And here's the logic is the beam is going to deflect like so. It has a curvature because there's a load here and then there's loads at the two ends from the reactions on this bearing. But afterwards, there's no loading. So the beam is not going to deform, right? It's just going to continue in a straight line with whatever slope we have over here. Well, we can use some trigonometry over here, right? Because this is just 1.5 is the original overhung length, right? And if we have this angle theta, we can use some trigonometry to figure out this guy over here as the side opposite to the angle theta. So first we'll calculate what this angle is. Excuse me, again, the equation is PL squared divided by 16 EI. So let's go ahead and put the values. P is 6.5 kilonewtons or 6,500 newtons. I'm pausing a little bit because I have the equation for delta max, but I forgot to walk you to looking at the units, right? So we have newtons on the top divided by newtons on the bottom. So that's going to cancel those right there. So newtons going to cancel with the newtons. And then we have meters squared times meters. So we're going to have meters cubed at the top. And then at the bottom, we have meters to the fourth divided by meters squared. So we have at the bottom, we have meters squared, right? So we have meters cubed divided by meters squared. So two of these cancel with one. And at the end, we just have a meter. So, okay. So now we're back to this one. In this one, we have 6,500 newtons. The length, L, be careful with this one, because if we look at the figure from the equations, I hope you can see it. The L is just the length of the beam between the two supports. So it's not going to be the full length of the beam. In this case, it's just between the two supports, which in this case is just 3 meters. This is going to get squared divided by 16 times 207 giga, or times 10 to the 9 Newton per meter squared, times I, which was 4.9087 times 10 to the minus 6 meters to the fourth. So again, let's make a unit check real quick. This new is going to cancel with this one. So at the top, we're going to have meters squared. If we look at the bottom, we have meters to the fourth divided by meters squared. So we have meters squared at the bottom, which is going to cancel with the meters squared at the top. And we're going to have something that is unitless. And not quite, right? If you remember, that equation is going to give the angle in radians. So all we have to do now is plug it in the calculator. 6,500 times the length, which is 3 meters squared, right? Divided by 16 times 207 e to the 9 times the I, which was 4.9087 e to the minus 6. Oh yeah. And we get 3.59 83 times 10 to the minus 3 radians. Okay, so that's the angle in radians. If we want, if we know the hypotenuse, right, this is just the original length of the beam, but when we push down, it bent up, right? So if I want to figure this opposite leg of the triangle, I take 1.5 times the sine of theta. So I can take 1.5 meters times the sine of this number. Just make sure the calculator is on radians, or we can convert this number to degrees, right? We can convert radians to degrees because we know, for example, that there's 180 degrees in pi radians. So 1 pi is 180. Remember when we have a circle, right? From here to here is 180 degrees, or just pi. A full circle is 2 pi or 360. Anyway, so we multiply this times 180 and then divide by pi. So times 180 divided by pi. This equals 0.20617 degrees. Again, you can use either or, but just make sure the calculator is using the right function. So here, I'm just going to calculate this height, right? This height of this triangle, which is essentially the deflection at A, right? So that height H is just going to be 1.5 times the sine of 0.20617 degree. So if I plug that in the calculator, 1.5 times the sine of 0.20617 20617, and my calculator is already in degrees. It gives me, let me write it in black, 5.3975 times 10 to the minus 3. What are my units? Well, I put 1.5. This has units of meters. So this is the same thing as a meter. Or if I convert it to millimeters, this is 5.3975 millimeters. What is the direction on this one? From our deflection curves, and I always advise to draw the deflection curve, this deflection is up, right? So this one is up, this deflection is down, right? So then what is the total? Well, we got 21.5 going down and 5.3975 going up, right? So the difference is 21.59, or we can do it like this, 5.3975, which is up, minus this one, which is down, 21.59, and it gives minus 16.19. So the total deflection, again, what did I do? Since this one is up in this class, I know when you go through solids, sometimes they tell you for a beam that is going down, for a beam that has a loading downwards, then the deflection downward is a positive deflection, and it gets all confusing. For the homework assignments for this class, we're just going to say, look, if a deflection is down, it'll be negative. If a deflection is up, then it's positive, right? So we're going to call positive for this class, 5.3975 minus, why minus? Because this one's opposite is going down, 21.59, and this gave minus 16.193 millimeters, or you can just say 16.193 millimeters down.